Thank you for joining us today and welcome to Astro 3D ECR Astronomers in Australia seminar series. My name is Anisha Harshan. I'm from the University of New South Wales in Sydney, Australia, and I'll be chairing today along with my co-chair, Dr. Jeffrey Simpson, also from the University of New South Wales. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today, and the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I'm speaking to you from the land of Bedegal people. My co-chair Jeffrey, as well as our second speaker, are joining us from the land of Wallumedegal clan. Our first speaker joins us from the land of Wurundjeri people of the Kulin Nation. We pay our respects to their elders, past and present, and extend that respect to all the First Peoples joining us here. This series is facilitated by ASTRO 3D, the Australian Research Council Centre of Excellence for All-Sky Astrophysics in 3 dimensions. COVID-19 has, of course, affected our ability to travel and to present at international seminars this year, and especially for us in Australia due to our time zone constraints. This series was created to provide opportunities to early career researchers in Australia to reach international audience and to try to mitigate this disadvantage. A few housekeeping things before we begin. There'll be 2 talks over this hour. Each will be 20 minutes in length and 5 minutes for questions at the end of each talk. I ask you to please save your questions until the end of each talk, or else feel free to use the chat function to ask your questions if you prefer, and Jeffrey can read them out. These talks are being recorded and will be placed in Astro 3D's YouTube channel. And by being here today, you are agreeing to abide by Astro 3D's meeting code of conduct. I've already warned the speakers about this, but because of the limitations of Zoom, I will need to interrupt the speakers verbally to indicate 5 minutes mark. Let's welcome our second speaker, Dr. Samyaday Choudhury from the Macquarie University, who will be telling us about photometric metallicity maps of Magellanic Clouds.
So hello everyone, I'm Samyaday. I'm a postdoc at Macquarie in Sydney, Australia. And I'll be talking to you about photometric metallicity maps of the Magellanic Clouds and what do they reveal, and the work that I'll be talking to you about has been done in collaboration with many people. There's Richard de Kreis, the VMC team with whom I'm working now, there's Annapurni Subramanian, Andrew Cole, Yong Jong Son, just ignore the mistake in Annapurni's name, it will be Subramaniam. Sorry about that. Okay, now we know that the Magellanic Cloud, the large Magellanic Cloud and the small Magellanic Cloud, they are our nearest pair of interacting galaxies. So they are morphologically irregular and they're gas rich and metal poor as compared to the Milky Way. The LMC is relatively metal rich as compared to the SMC, and these 2 galaxies, they are lying at a distance of 50 to 60 kiloparsec and at high galactic latitude. So they suffer pretty less from extinction due to the galactic disk, so you can actually resolve their individual stellar population, and you can detect faint stellar population in them. And so for several years, the clouds, they have been ideal test beds to study star formation, stellar evolution, or star clusters in a different physical and chemical environment outside our galaxy. Now, as I told you, the interesting thing about the Magellanic Clouds, the LMC and the SMC, are that they are interacting with each other as well as with the Milky Way. So they were previously believed to be, have gone multiple orbits around our galaxy, but HST proper motion studies in the last decade or so suggest that they are having their first infall towards the Milky Way. And you can see various signatures of interaction there in gas as well as in stars. There's a Magellanic Bridge, and then there's a stream of gas, the leading arms. So these are all signatures of interaction. And apart from that, even the structures, there are several structures and substructures in the main body and outer periphery of the clouds in the stellar population, which is due to their periodic interaction. Now, one way to understand, so we are still trying to understand the evolution and interaction history of these clouds. And one of the ways is to understand the spatial distribution of metallicity, or the metallicity gradient. Now, the ideal way is actually to do spectroscopic studies, but uh, uh, we can understand that no, it will be a mammoth task to do a spectroscopic study of billions of stars. It will be time consuming. At the same time, it will be uh, not economical. So an alternate way is large area photometric surveys. So the previous studies have, which had focused on doing calcium, say calcium triplet spectroscopic study of RGB stars in the Magellanic Clouds. So most of them have been confined to small pockets within these galaxies, uh, or if there were photometric studies, there was an inconsistency between the tracers and calibrators that was used. So basically, to understand the nature of the gradients in these two galaxies till large radii beyond their main body, it needs photometric data in that sense are a savior. Uh, and in 2016, we came up with the first of its kind high spatial resolution metallicity map for the LMC, and followed it with the SMC's work in 2018, where we created these maps by combining photometric and spectroscopic data of uh, RGB stars. Okay, so the tracers and calibrators were same. And very recently, Grady et al. They employed machine learning technique, which is different from that of ours, but even they were combining photometric estimates with spectroscopic studies. Now, I'll be talking about the work that we have been doing since 2016. So, for the 2016 and 18 work, the data that we used was optical photometric data, V and I band, from the UGL 3 and the MCPS survey, which were surveys. So, these were using a 1 meter class telescope of the Magellanic Clouds. And since the last uh, 2 years or so, we have been creating this metallicity maps using the near infrared passband data from the VMC uh, Vista survey. So, which is basically a near infrared survey of the Magellanic Clouds using the 4 meter Vista telescope at Parnell. So, I'll be talking on that. So, okay, this is just the VMC Vista view of the LMC. Now, so what is the technique that we use? I'll just tell you briefly about it. So, so we divide the galaxy into small areas spatially based on their stellar density, and this is the color magnitude diagram of one such small region. So basically, evolved stars, the stars which have evolved of the main sequence, say red clump stars or RGB stars or AGBs, they can be used as tracers to understand uh, their evolution and interaction. So in this case, we are using the RGB stars. This is Y versus Y minus uh, K color magnitude diagram. And the advantage of near infrared passbands over optical is that the RGB stars, they are brighter in near infrared wavelengths. At the same time, uh, the tool that we are using the slope of the red giant branch as an indicator of metallicity. So I just want you to remember that if the a region in the galaxy is metal rich, the RGB slope will be shallow. It will be more tilted towards the color axis. If it is metal poor, it will be, you know, shifted away from the color axis. So this is the technique that we use. And in near infrared CMDs, the uh, RGB is more like a straight line as compared to optical, where it's sort of curved, so it's easier to estimate the slope. So basically, we developed this technique where you isolate the evolved part of the color magnitude diagram, and then you identify the most dominant part or the most dominant RGB population for that region in the galaxy and estimate its slope. And the method is such that it's independent of reddening and distance variation, and you can automate it over the few thousands of uh, you know spatial bins that you have divided the galaxy into. Okay, so after doing that, after estimating the slopes, we convert the slopes to metallicity using spectroscopic estimates. So in this work, for example, as well as in so this is a recent work that we are about to submit using the VMC survey, and this is the calibration relationship of slope and metallicity in our 2016 work. So in both the cases, we used calcium triplet spectroscopic data from Andrew Cole's group from their previous work. And basically, we map the mean metallicity of a region uh, with of we found out the mean metallicity by sort of averaging over the spectroscopic red giants which are falling in that region, and we map it with the slope of that region. So for the selected regions, we use them to uh, find out this empirical relationship between slope and metallicity, and calibrate our slope maps. Now, this is the resulting metallicity maps of the large Magellanic Cloud. The one below is from the VMC survey. So you can see that the bar region is metal rich, and the outliers, the outer regions, are actually relatively metal poor. But the gradient, the variation is not as strong as that we had seen in the maps using Google and MCPS data, which are above. So you see a more uh, drastic variation there. Okay, and similarly, in similar variation was seen even by Grady et al. In their recent work. So, however, there are a lot of regions for which we couldn't estimate metallicity in the optical maps. So these are regions which are suffered due to either multiple dominant population or star forming region, for example, the 32 radius region. So we couldn't estimate them in optical maps, but we are able to the maps using near infrared data are more or less uh, relatively more homogeneous as compared to optical maps. At the same time, we cover at least 2 to 3 times larger area as compared to the Google and MCPS maps. Now, okay, this goes on to show the comparison of metallicity distribution, and we find that the distribution in the bar region is more narrower as compared to those in the outer region. At the same time, it again sort of highlights that the bar is indeed metal rich as compared to the outer part. And this shows the comparison of metallicity gradient of the Large Magellanic Cloud from our 2016 work and our recent work. So the gradients that we estimated using optical uh, surveys, it agrees well with that of previous works and as well as that of Grady. But with VMC near infrared passband, though we are able to sort of estimate it a larger radii, but it's more or less negligible or very shallow as compared to what we uh, estimated using optical studies, though they more or less agree within the error. So well but overall, qualitatively, the NIR trends are qualitatively similar with that of optical studies. Like you see a metal rich bar region to 2.5 kpc, and then there is a dip after that. And the result that we get in this study using NIR passbands is very similar to the star formation history study by again using similar passbands from the BMC survey by Mazi et al. It's an upcoming paper from the BMC team. Uh, Even they didn't find much variation in metallicity within the LMC from their studies, and they owe it to probably the insensitivity of the near infrared passbands to metallicity or systematic effect. We also estimated the radial metallicity gradient in 4 different directions, and we find that the gradient in the direction in the southwest direction, which is in the direction of the bridge and the SMC, it's metal poor and relatively flatter as compared to the other 3 directions. Talking about the SMC now, any metallicity variation in the SMC was much debated uh, in previous studies that used various stellar populations and various techniques. So we employed a similar technique for uh, RGB slope estimation, and you can see the calibration relation in the left side is shows the relation that we had got in 2018 work, and this is for the work which we published last year using the near infrared pass bands. So we have at least, I think, 3 times more calibration data as compared to 2018 work. And here's the SMC Metallicity Map. So what we find is from both NIR and optical that there is indeed a shallow gradient till 2 to 2.5 kiloparsec. We see some metal rich region in beyond, -3 or +3 uh, degrees, which could be artifacts, but such regions are, very less, 3% of the total sample, so it's very less. And this shallow metallicity gradient is also found out by Grady et al. In their work, though they don't comment on the value because the structure of SMC is uh, very different. It's a very complicated structure. We don't understand it well. It has a large line of sight depth. So how we find out is, we generally, in consistence with previous studies, we just uh, assume it to be an ellipse where the major axis is along the north east direction, and then we estimate the gradient. Whereas LMC has a more relatively simpler structure. It's more like a face-on galaxy, and you can find out the gradient by assuming it to be like a thin disk.
Samyaday, that's the 5-minute mark.
Okay, yeah, thank you. So this is just reinstating what I mentioned. So the shallow gradient that we found is very consistent with what spectroscopic study has found by Doby et al. Or Parsi et al. And so we couldn't comment much. So the metallicity is beyond 3 degree, 3 to 4 degree, which see a very flat trend, but since the dispersions were pretty high, we don't comment much about those that trend beyond 3 to 4 degrees. Uh, and what we detect is we also detected a asymmetric radial metallicity gradient, where we find that the eastern part of the SMC is flatter. The gradient in the eastern part is flatter as compared to that in the west. Okay, so eastern part is basically the direction of the bridge and the LMC. Now, coming to the implications. So first of all, the shallow gradient that we estimated using optical studies, it shows that the LMC's gradient, though shallow, it's very similar to what's seen in spiral galaxies like that of ours. Okay, and the NIR maps, though the gradient is very shallow, almost negligible as compared to optical, they qualitatively reproduce the same global metallicity features like a homogeneous and metal rich bar and decreasing metallicity in as you go outside the galaxy. So sort of it says that the bar might have played its role in mixing the metal rich population in the center, and this, we don't understand the LMC's bar pretty well. It's a stellar bar. We're still trying to understand it. So the bar role of the bar is probably consistent with what with studies on barred galaxies tell us, that it is efficient in radially mixing the stellar population. Uh, and we the asymmetric gradient that we detect in the southwest part of the LMC is possibly an analog of a similar trend that we see in the eastern SMC, and probably a result of stellar mixing which is happening as a result of tidal interaction between the LMC and the SMC. Uh, and Talking about the SMC map, yes, our studies does confirm the existence of a shallow metallicity gradient within 2.5 degrees of the SMC. That is the inner SMC. It's probably because the more metal rich and young stars are centrally located, and we see this flattening beyond 3 degrees, 3 to 4 degrees. We don't quantify it, and we still need to understand what could have caused that shallow trend. We don't know much about any bar in the SMC. Yosin and Vicky, 2014, they talk about a weak bar in the SMC. So is it because of that, or because of the interaction of the LMC and SMC system in producing this shallow gradient and then flattening at the outer radii? This needs further investigation. I already talked about uh, the similarity in trends in southwestern LMC and eastern SMC, which probably indicates the tidal interaction. Uh, well, in future, we are looking to extend the metallicity estimation to the bridge and outer peripheries of the cloud by combining multi-wavelength photometric data, uh, astrometric data, as well as available spectroscopic data, and of course, facilities like upcoming facilities like Foremost are very important to sort of understand the individual chemical abundances or chemokinetics of specific regions in the clouds, uh, which can give us a better understanding of the evolution and interaction history of the clouds. So thank you for your attention.
Great. Thank you so much for this great talk, Samyaday. Jeffrey, do you have any questions?
Are there any questions from the audience? Feel free to raise your hand or type them into the chat. I'll start with, I think you commented it in your conclusions, but I was wondering about actual spectroscopic follow-up on things like, I know that Apogee has a sample of Magellanic Cloud stars. That was putting on my Galar hat, but unfortunately Galar, we really struggle in the Magellanic Clouds because we only get like the very top of the giant branch, and so they're pretty not the best stars in the world. But I was curious to know what the sort of pure spectroscopic metallicity follow-up was going to be like now with these large surveys coming along.
So I'm just trying to understand your question. So are you asking why we didn't use Apogee? Or?
Well, it's more thinking like, in terms of like Apogee, is there actually enough stars in Apogee to sort of say anything useful along the lines you're doing?
Yeah, I mean, for example, the work of Grady et al., they use Apogee data to do their analysis, and they combine it with photometric surveys like Gaia and TUMAS and OIs. And I tried using Apogee, but the Apogee sample turned out to be insufficient for me in getting a calibration relationship. So using my technique, it's difficult. I found it to be difficult, but probably there are other ways to incorporate Apogee. I mean, we have to wait for Foremost to come up, but probably we need to think of a smarter way to use up uh, the Apogee data actually. I don't know, Galar doesn't help much, as you said. with
No.
respect to the RGB, maybe AGBs and all.
Yeah, it's basically it's the magnitude limit. We go to the 14th magnitude, and that's getting you to the very, very top of the giant branch. And apogee, maybe gets you the 15th or 16th magnitude
maybe
apparent.
12 to 14 magnitudes.
Yeah.
Yes.
Other questions? I can ask a slightly technical question of how did you come up with the regions when you were sort of grouping into your images into little chunks to do the color magnitude diagrams? How were you picking them?
Okay. Let me see if I have a slide for that.
Is it basically sort of random or grid? I think some of it was gridded.
It's basically dividing them based on stellar density, actually. So is my screen visible?
Yeah.
Okay, so if you can see this, we basically try to keep the RGB similarly populated across all the regions that we consider. So the central regions of the galaxy, for example, which are high in stellar density, they are more finely built, so that we end up with a similar range in the RGB.
Okay.
So yeah, it's basically binning them. I mean, if you can see this, if in this table, n is the number of stars in a particular region. So more the number of stars, and this shows the number of divisions along RA and DEC. So as we go to higher density, stellar density region, so the binning becomes finer in RA and DEC. So it's completely based on stellar density. I don't know if, if that answers your question.
Yeah, I guess you could. You wouldn't necessarily get a different answer if you all shifted. Like you could come up with a different tiling pattern, but it should give you the same answer.
Yeah. There can be more smarter ways of sort of considering the areas. I mean, you can probably start with one and then keep on expanding. But yeah, the idea is basically to keep similar number of stars in your RGB, maybe within certain areas, but yes.
We have a question from Roger.
So I hope you haven't already answered this because I got slightly interrupted for a couple of minutes in the middle. But these stars that you're using, presumably, are there any of these stars in common with the ogle stars? Have you compared the metallicities that they get and publish compared to what you get and publish for the same stars? Is that something that's possible?
Oh, okay. So the work on ogle and MCPS that I showed, it's my work only. So yes, I mean, if you, so I'm trying to understand your question.
Well, okay, so maybe even more specific, right? If I understood correctly, and I may have misunderstood, ogle finds, working at optical wavelengths, finds a slightly steeper gradient than you do, working at infrared wavelengths, right?
Yeah.
Yeah. So the question is, some of those stars are presumably the same stars, they're in common, right? So there must be two measurements of the metallicity, one in the infrared and one in the optical. So so why are they different is the question really, and what do you learn from that?
Okay. Yeah. So though the method that was used for optical and near infrared, the method was same, the area binning criteria for the surveys were different because we were using different kinds of data and different wavelengths.
Yeah.
So one reason could have been because the size of the areas that we consider in near infrared are little larger as compared to the optical surveys. But we checked if there is an effect of area or not, but we find that there is no effect of areas. So overall, what we are interested in is looking at the relative variation between regions, and not
Yeah.
the metallicity of particular of metallicity of that particular region, original metallicity. And we think that it's possibly because of the insensitivity of the NIR passbands to metallicity. Uh, it's I think it's more because of systematic effects that we are getting a shallower gradient in NIR passbands.
Okay, thank you.